The final minutes of a falling machine were a thin white line across a black screen. Static fluttered, then steadied, then crackled again as the antenna scraped the edge of a giant world's atmosphere. You could almost feel the body tilt. You could almost hear the rails of gravity hum. The planet filled the view, a pale rim curving like a blade of ice. Bands slid beneath the craft in slow rivers. A narrow gap opened between the cloud tops and the rings, and the machine threaded it, counting grains, counting fields, counting seconds. It wrote while it burned. It sent a last breath through a sky that has never known breath. At the north pole of that world, something angular turned with a calm that mocked weather. 6 long walls of cloud made a hexagon you could fit continents inside. The edges held. The corners held. It came back year after year as if printed into the air. The paradox arrived in the same frame. Meteorology loves chaos. Yet here was a shape that refused to fray. We expected drift. We expected wobble. And still the pattern returned like a metronome you could stare at from orbit. Close by. A second riddle waited. We had counted the planet's day by radio signals. Then the clock slipped. Days stretched or shrank in a way no spinning globe of gas could explain. Was the world changing speed, or were we mistaking a flicker for a tick? If the rock or metal at the core does not speed up, what does it mean when the time you measure does? Farther from the sun, where light is poor and the solar wind thins. Another world drove its air nearly as fast as sound. The color was deep blue. The heat budget was thin. Yet winds raged. They circled the globe like a dark river pressed against the sky. Here the ledger of energy refused to balance. The lamp is dim, yet the dance is wild. Sailors of cloud lean into a gale that seems to come from nowhere. Where does that power come from? How can a cold world drive hot motion? Closer to the rings, the camera saw a different kind of music. The rings were pale and bright in stretches, then smoky and quiet in others. Ripples crossed them like fingerprints. A small moon crossed, left a wake, and vanished into glare. The ripples did not fade. They traveled, echoed, intersected, and told us a strange story. The rings were not passive. They were a drumhead, stretched and tuned by gravity. They were a phonograph groove, written by a hand we could not see. If a planet hums in its deep interior, gravity carries that hum outward. The rings answer with waves. Count the spacing. Match the rhythm. A day emerges from ice and shadow, not from a dial on a dashboard. You have time to train by its shadow on a wall. You have counted heartbeats by resting a hand on a wrist. We can time a world by counting ripples that slide through frozen grains too small to name. That is the promise that rose from those last passes, when the craft slipped between the planet and the rings, then surfaced again, then slipped through once more, with the usual noise reduced. The gravity field spoke with a cleaner voice. Where it swelled and sagged, the rings shifted. In those shifts lay the pace of the interior, the twist of the layers, the difference between a day made of radio and a day made of mass. Now look at the light near the poles. Curtains of green and purple circle the dark. They brighten, dim, and brighten again. They mark lines we cannot see, lines the planet draws through space when its field takes charged particles and flings them into the air. Those lights are not just beautiful. They are wires in the planetary circuit. In that high, thin sky, particles dump energy the way sparks fall on dry grass. The upper atmosphere warms more than sunlight alone can explain. The planet shines more heat than it receives. Something else is paying the bill. A long circuit may be the reason. A loop that runs from rings to moons to field to air, and back again. If that loop is real, then the poles are not just the ends of a magnet. They are radiators. They are engines at the top of the world. The field that guides those lights carries a deeper puzzle. On this planet, The magnetic axis sits almost on top of the spin axis. Many dynamos prefer a lean. They like a misalignment that lets their heaving metal write a broad signature through space. Here, alignment is close to perfect. Perhaps the field is edited before it reaches our instruments. A conductive layer in the sky may polish the roughness and hide a small tilt. Perhaps different layers inside the planet spin at slightly different rates, like nested gears, changing the radio glow we trusted as a clock. The closer we place our ear, the more careful we must be about what counts as a tick. At its core, we are not just collecting pictures of weather, we are testing how giants breathe electricity and time. We ask whether rings can remember, whether auroras can heat, whether a field can lie to a magnetometer without lying to a storm. The questions are not trivia. They decide what we expect around other stars. They shape how we design craft to survive near massive worlds that guard and wound in the same gesture. Watch the belt lines. They look calm from a distance. Then a storm lifts a tower, and the tower tilts, shears, and stretches until it feeds a river that wraps the world. On one world, a long red scar narrowed, paled, then flared again, as if a lighthouse had blinked in fog for a century and then found clear air. On another, a white spot rose from nowhere and died in weeks, as if a breath had fogged a window and then faded. These are not moods. They are responses to heat that moves in layers and to a spin that shapes every line of flow. They are the signatures of engines we cannot see, turned into motion we can see. Think about the sideways world, the one that rolls like a barrel while circling the sun. It presents a pole to the light for decades, then the other pole, then returns to twilight. Seasons are measured in the lives of people. If an ancient blow toppled that world, the echo of the blow still runs through its climate. The equator sulks. The poles feast. Diffuse heat builds in places you would not expect, then drifts. A toppled spin rewrites weather. What does that teach us about deep energy? What does it teach us about the long, slow bleeding of heat into space? Now return to the craft that dared the gap. The air was thin. The dust was less than expected. The fields were strong and changeable. Each pass wrote a line in the log. The lines were measurements of gravity, of plasma, of dust grains flicking at the hull like rain. At the end, the craft did not swing wide for a safe exit. It dove. It surrendered mass to gain a moment of clean data. It offered a body to the furnace, so we could know the taste of the air and the feel of the field where no spacecraft had flown. That choice is not a flourish. It is the core of the method. To know a giant, you go where giants live, and you pay in machines. We care because meaning follows measurement. If rings can be read as a seismograph, then we can place the interior rotation rate with a precision that forces models to choose between rival pictures of the deep. If auroras raise the temperature of the upper air by channels we can track, then we can budget energy with numbers instead of adjectives. If field alignment is real and persistent, we must ask what kind of dynamo can give it. If it is a trick of the atmosphere, then we have to model that trick and subtract it before we call a day a day. The hook is not a slogan. It is an image and a paradox in the same breath. The image is a ring system rippling when a hidden hand plucks a string. The paradox is a clock that drifts while the world that holds it is too massive to twitch so quickly. The large question follows naturally. What engines run the giants? Are they only deep and hot, or also high and wired? Are the rings ornaments, or are they archives of motion? What does it mean for our own system if the guardians in the outer dark can both shield and scar? We will not answer by charm. We will answer by 3 lines of evidence. We will follow the rings as they store beats from the interior, and we will read those beats as time. We will follow the polar lights as they carry power from circuits that do not care about sunlight, and we will count that power in degrees. We will follow the axes and the fields as they line up or lean, and we will decide whether alignment is a property of the engine or a mask across its face. Each line will open a door. Behind each door will be a room with numbers on the walls. There is a human scale to this. You have counted your own steps in the dark to measure a hallway. You have used a reflection in a window to see a face behind you. You have pressed your ear to a door and heard the thrum of a washing machine through wood and air. The science here is the same act, scaled to worlds. We hold still. We count. We compare. We learn to ignore the first obvious clock if that clock is tied to weather or charged gas, and we learn to trust the one that responds to gravity alone. There is also a cost. When the craft fell, the signal narrowed to a thread. Bits arrived. Bits failed. The line broke. The planet accepted the body without a mark. No smoke rose. No scar remained. But in the tall stack of numbers the craft sent before the line died, there are pieces of the puzzle that did not exist a day before. That is how knowledge walks forward at the edge of the solar wind. It trades stories for spectra. It trades safe return for clean data. It trades the idea of a planet for the weight of a number you can write and test. The open loop is set. The rings will give us time. The auroras will give us heat. The axes and their fields will give us the map of the engine that turns a sky into a weather factory. Follow these three, and the paradox that looked like a taunt will become a picture we can point to and say, this is how a giant breathes. If this investigation speaks to you, please like and subscribe to the Quiet Universe channel. From far away, the rings of a gas giant look like light, a smooth halo, unbroken, timeless. But close in, that halo becomes millions of threads, each grain tracing a story of collisions, resonances, and tides. When the cameras of the passing spacecraft began to resolve those details, scientists saw something that no model predicted. The rings were trembling. Faint ripples rolled across the bands as if a drum were being struck from below. Those tremors were not noise. They were signals. They formed spirals that could only be explained if the planet itself was vibrating, not in the way an earthquake shakes Earth, but through long, slow pulsations that traveled through metallic hydrogen and deep currents. Those vibrations tugged at gravity, and gravity tugged at the rings. Each wave in the ice was a heartbeat of the world. Each crest was a mark of time, drawn not on rock or metal, but on snow dust circling in the void. Imagine looking down on that disk. One arc brightens, another fades. Small shepherd moons carve edges so sharp they could slice shadow. Every particle moves in the rhythm of a planet that breathes heat from its core and exhales it into space. Yet the rhythm is not steady. Where theory predicted clean frequencies, the rings play a mixed tune. Some tones stretch, others vanish. The mystery is simple to state and hard to solve. How does a world so large sing a song that drifts with the years? We use waves as clocks because waves carry memory. On Earth, you can trace earthquakes through the planet by timing their echoes. In the same way, you can time the interior of a gas giant by studying how its gravity imprints on its rings. This technique, called ring seismology, let us listen to a world we cannot touch. The ripples are faint, but their spacing carries the story of the deep. The trick is to count them carefully and to believe that what looks like decoration is in fact data. In plain terms, the rings are a seismograph spread across 100,000 kilometers of space. Each disturbance records a vibration in the body below. The larger the planet's internal motion, the more pronounced the wave. By mapping these ripples, scientists can measure how fast the inner layers rotate, and from that infer the true length of a day. When they did, they found a surprise. The day defined by the rings was shorter than the day defined by radio pulses. The two clocks disagreed. Either the atmosphere cheats, or the planet hides a second rhythm we have yet to isolate. Think of a phonograph. The needle rides a groove carved by sound. Here, the groove is carved by gravity. The pattern that emerges is ancient but not fixed. Moons pass and modulate the beat. Each passage writes a new overprint, a remix of the past. Over billions of years, those waves erase and rewrite themselves. But traces linger. Reading the rings is like listening to a record while it is being recorded. You hear the present, but you also hear ghosts of older songs. Why does this matter? Because knowing the true rotation of a giant world is like knowing the tick of a clock that sets the time for its entire system. The winds, the storms, even the magnetic field depend on that spin. Without it, models wander. If we can measure a planet's heartbeat through its rings, we can anchor every other variable that depends on time. It is like finding the hidden metronome behind a symphony. The patterns also tell us about age. Some ripples fade quickly. Others persist for centuries. When we compare the rate of decay to the expected collisions among ring particles, the story turns darker. The rings may not last forever. They are slowly raining onto the planet, a drizzle of ice vapor and dust. If they are ephemeral, then we live at a rare moment, one where a planet wears a visible clock around its waist before it melts away. It is as if we arrived at the last performance of a concert that has been playing for billions of years. Inside those ripples lie deeper puzzles. Each oscillation mode corresponds to a region within the planet, like notes in a chord. Some modes do not match any theory. They suggest the interior may be layered in ways our models never considered, perhaps with zones that rotate at different speeds. That could explain why radio and ring time drift apart. The planet may be a machine with two sets of gears, each turning slightly out of sync. What we measure from above depends on which gear our instrument happens to touch. If that is true, then the rings are a translator. They convert motions too deep for light or magnetism into language we can see. Every wave crest is a word. Every pattern is a sentence about pressure, density, and rotation. All we must do is learn to read. One day, a probe dove through the narrow gap between the inner rings and the cloud tops. The craft counted grains with its radio instruments. It mapped gravity with tiny variations in speed. Each orbit peeled back another layer of the unknown. The field was not smooth. It pulsed. The shape of those pulses confirmed what the rings had whispered for decades. The core is diffuse, not solid. The boundary between metal hydrogen and molecular hydrogen blurs. A slow churn moves heat outward. The rings echo that motion like a drum skin pressed by invisible hands. You can see the human side of this too. To read those ripples, we rely on computers comparing patterns so faint they might as well be whispers. It is a kind of archaeology with light. Dust stands in for bone. Gravity stands in for story. The more precisely we listen, the more alive the planet becomes. Not as myth, but as rhythm. What if the rings could tell us more than time? Some researchers suggest they might also record changes in the magnetic field, since charged particles in the rings respond to electric variations. If true, we could map not only the planet's spin, but also its heartbeat of magnetism. Seeing how storms in the atmosphere couple to flows in the core, that would turn the rings into the most detailed observatory in the solar system, a silent archive of every tremor the giant has ever made. When you look at the rings tonight through a telescope, you are seeing the outermost skin of a planet's pulse. Those bright arcs are moving faster than bullets, yet to your eye they seem frozen. Their stillness is an illusion born of scale. In the gaps, small moons herd the ice, keeping orbits tidy. Those moons feel the pull of larger moons farther out, which in turn respond to the gravitational rhythm of the planet itself. The whole structure is locked in resonance, a harmony that only looks calm. Underneath it all, the giant's deep breathing keeps time. Meaning hides in that rhythm. By matching wave patterns to models, we can tell how much heat the planet retains from its birth, how quickly it cools, and how long it might keep glowing in the infrared. That information feeds into our understanding of planets around other stars. If the giants of our system can serve as standards, then distant rings, seen only as smudges of light, could reveal the ages and spins of alien worlds. In plain terms, Every bright arc is a data line, every gap a pause between phrases. The rings remember what the planet would otherwise keep secret. They are an open notebook written in ice. We are the readers, tracing each curve with instruments and patience, hoping not to smudge the ink. The more we learn, the more the rings look alive. They are not the relics of creation, but the instruments of an ongoing conversation between gravity and time. Each particle is a memory grain, each orbit a syllable. Together they make a script that only light and gravity can read. The planet writes without hands, and the rings repeat its motion until they fall. It is hard not to feel awe at the scale of that recording. Human time spans blink compared to one cycle of those waves. Yet the same physics that moves oceans on Earth moves the icy dust of a ring hundreds of millions of kilometers away. We are connected by equations older than the solar system itself. If you ever doubt that silence can carry meaning, look at those arcs again. They make no sound, yet they hold the longest song in the sky. Each ripple is a note left behind by a planet's unseen hand. Each beat reminds us that the universe keeps time even when no one is listening. And if rings can hold memory, then what might auroras hold? Those curtains of charged light that rise where the magnetic field meets the sky. High above the pale clouds of the giant world, a strange glow ripples across the night side. Curtains of light curve along magnetic lines, green and violet arcs sweeping the poles. To the human eye, they look like the auroras of Earth. But here they stretch for tens of thousands of kilometers. They appear where sunlight cannot reach, where cold should reign, yet the air there burns with heat that no starbeam provides. When the first measurements came back, the numbers made little sense. The upper atmosphere was hundreds of degrees hotter than models allowed. Radiation from the distant sun was too weak. Internal heat could not rise that far before radiating away. Something else was feeding the flame. It glowed brightest where magnetic fields met the charged particles coming from the rings and the moons. The pattern matched the auroras. A planet so cold that hydrogen freezes in its shadows was lighting a fire at its edge. At its core, the puzzle was one of balance. Every planet should settle into an equilibrium between sunlight absorbed and heat radiated. This one did not. The extra warmth suggested a secret current of energy, one running through invisible wires drawn by magnetism. The data from ultraviolet and infrared instruments confirmed the excess. At the poles, the glow flickered like a signal, fluctuating with the rhythm of the planet's rotation. The same field that sculpts the rings and guides the particles seems to inject energy into the air, turning the thin gas into a kind of plasma lamp. You can picture it like a vast electric circuit. The planet's rotation drags magnetic field lines through space. Those lines cut across clouds of charged particles. The motion drives currents, and those currents pour energy into the upper atmosphere. The result is a cold flame, a region too rarefied to sustain fire as we know it, but bright and hot in its own way. Where Earth's auroras dance briefly, the giants burn steadily, fusing color with invisible heat. Simply put, the air glows because gravity and magnetism cooperate to turn motion into warmth. Each turn of the planet twists the magnetic field, which in turn whips electrons into spirals that crash into atoms high above the clouds. The collisions release light, but they also release heat that stays trapped, building an invisible furnace. It is as if the planet carries a pilot light above its storms, a steady blue fire no sunlight could ever ignite. Why should we care about this? Because the mystery of energy balance touches the oldest questions in planetary science. If we can explain where the excess heat comes from here, we might understand why many giant exoplanets also glow hotter than they should. Some of those far worlds orbit close to their stars. Others drift in the cold. Yet both radiate more energy than they receive. The cold flame over Saturn or Jupiter might be a local version of a universal rule. Consider what this heat means for the planet's weather. Warm air expands, drives circulation, and alters wind speeds. The upper layers act as the lid of a pressure cooker. When they warm, The layers below must respond. Models show that even a few percent of extra heat can amplify storms or extend their lifetimes. A localized glow at the poles could influence entire belts near the equator. The planet's winds are not random. They are the expression of deep electrical breathing. One spacecraft captured a view of those auroral ovals shifting in sync with radio emissions. When the radio waves change, the lights brighten or fade. That coupling proves that the magnetic field carries more than particles. It carries timing. Each pulse marks the passage of energy from the deep interior to the rim of space. We can treat the glow as a real-time indicator of the planet's internal rhythm. It is like watching the heart of a giant through the shimmer of its crown. Why do the poles host this phenomenon? Because that is where the magnetic field opens to space, letting charged particles spiral inward. Moons that orbit within the field contribute as well. They shed material, ionized by sunlight or collisions, feeding the system like fuel added to a flame. The most active of these moons sprays jets of water vapor that break into ions. Those ions travel along field lines until they strike the atmosphere, releasing heat where cold should rule. Some researchers suspect that this process links directly to the rings. Dust and ions lifted from the ring's inner edge could join the same magnetic highways, forming an electrical loop from ring to atmosphere and back. The data from particle detectors support the idea. The composition of the upper air matches the elements found in ring material. It is as if the planet's crown fire runs on the ashes of its own halo. At first glance, the heat might seem trivial, a few hundred degrees in a realm where storms reach thousands. Yet the difference is critical. That warmth changes the chemistry of the high air, allowing molecules to form or break apart that would otherwise stay inert. It alters the spectrum we see from Earth, changing how much infrared light the planet emits. In turn, that emission shapes our sense of its age and energy budget. A small adjustment in temperature rewrites the entire story of the planet's evolution. There is a human-scale analogy. Stand near a power line on a foggy night and watch the blue corona form around the wires. The air is cold, but it glows where the field is strongest. The same physics applies, only scaled beyond imagination. The cold flame above the clouds is a planetary corona, humming with power, turning motion into light. In everyday language, the giant's atmosphere behaves like a dynamo that reaches all the way into space. It converts rotation and magnetic drag into an upward flow of heat. This process blurs the line between meteorology and astrophysics. The weather does not end at the top of the clouds. It continues through magnetism into the vacuum. There are competing views. Some teams propose that the energy comes not from currents but from waves rising through the atmosphere, the upward echoes of storms below. These waves could break high above, releasing their momentum as heat. Others argue for particle precipitation alone. The truth may combine both. Gravity waves could modulate the field, making it easier for particles to enter and harder to leave, creating a rhythm that matches the radio pulses. The evidence is suggestive, but not final. What matters is that we now have a way to measure it. If this theory holds, the cold flame explains why some gas giants radiate more energy than their mass and distance predict. It may also hint at how early planets cooled after formation. When a world is new and full of leftover heat, these magnetic and atmospheric interactions could regulate how fast it loses energy. The cold flame could be a thermostat written into the laws of motion and charge. You can almost see it, a slow-motion fire burning at the edge of darkness, fed by particles drawn from a ring of ice. It brightens and fades with the planet's day. To anyone watching from above, it would look like a faint halo surrounding the poles, its edges tracing invisible wires into the void. It is beautiful and silent, a reminder that even in the coldest reaches of the system, energy finds a way to move. The deeper meaning is simple. A planet is not a sealed sphere. It is a network of flows: heat, light, magnetism, and motion. The cold flame above the clouds is proof of that unity. It shows that the smallest particle and the largest field belong to the same conversation. Understanding that conversation is not just an act of curiosity, it refines our search for life, because every habitable world must manage its own energy balance. If magnetism can feed warmth into an atmosphere here, perhaps similar currents keep distant planets temperate enough for chemistry to begin. We measure these auroras not only to admire them, but to learn how nature distributes energy when sunlight is scarce. Even now, new data keep arriving. Each orbit of a probe refines the temperature map of the upper air. The hot spots drift, vanish, and reappear. The flame breathes. We are watching the metabolism of a giant, a living diagram of how motion becomes light. Where there is light, there is a clue. The next clue hides beneath the glow, where the magnetic field meets the deep interior and mirrors itself in ways that challenge our sense of symmetry. A magnetic field is a planet's reflection, an invisible mirror showing how its interior moves. Deep inside a gas giant, where pressures crush atoms and hydrogen becomes a metal, motion and heat generate electricity. That electricity folds back on itself, creating a magnetic shell that extends into space. On Earth, the magnetic axis tilts from the spin axis by several degrees. On Jupiter, the tilt is even larger, a lively mismatch that makes sense in dynamo theory. But then came Saturn, a world that seemed to break the mirror. Its field and spin appear almost perfectly aligned. At first, the discovery looked elegant, a field so symmetrical that the planet's poles nearly overlapped on every map. Instruments found barely a fraction of a degree between them. Yet elegance quickly became contradiction. The dynamo equations that govern planetary magnetism require asymmetry. The lean is the lever that allows the field to change, to pulse, to sustain itself. Perfect alignment should cause the dynamo to fade. In a flawless mirror, no current can find a foothold. So if Saturn's field is truly straight, how does the current still flow? The spacecraft that circled the planet measured the magnetic field over many orbits. Slicing through different latitudes, the data stayed steady. No tilt appeared, no wobble large enough to explain the dynamo's endurance. To resolve the paradox, some scientists propose that we are seeing only a filtered version of the field. Perhaps a conductive layer in the atmosphere smooths the rough edges, hiding the true tilt beneath. Like frosted glass that turns a bulb into a featureless glow, the outer envelope may blur the details of the magnetism below. In plain terms, the field might not be truly symmetrical. We may simply be looking at it through a fog of charged gas. That fog could edit the signal, erasing imperfections the way a calm lake erases ripples after a stone sinks. If so, the real magnetic poles could wander deep inside, unseen and misaligned. Only the smoothed copy reaches our instruments. The visible field is the planet's public face, a polished reflection that conceals its motion beneath. The concept is difficult because it contradicts intuition. A magnetic field is not fixed like a bar magnet. It is a moving sea. Within that sea, molten hydrogen flows and twists, producing loops of current. When these loops lean, they create north and south poles that are offset from the spin. When they align perfectly, the currents lose the ability to regenerate the field, and the system should decay. Yet Saturn's field remains strong, which means some internal complexity must sustain it. Think of watching a fan through a window screen. The blades spin, but the pattern you see flickers differently from the motion behind the mesh. Layers between the source and the observer distort the rhythm. Here, the fan is the dynamo. The mesh is the ionosphere. The distortion gives us a reading that looks steady, even if the true motion is restless. Why does this matter? Because magnetic fields are more than curiosities. They shield atmospheres from radiation and sculpt entire systems of moons and rings. Without them, charged particles from the sun would strip lighter gases into space. The shape and strength of a field determine what a planet keeps and what it loses. Understanding the symmetry of the field means understanding how a planet evolves, breathes, and protects itself. The radio emissions that define the planet's day also tie into this mystery. As the field rotates, it drives radio waves from charged particles spiraling along its lines. Those radio periods once served as our clock for the planet's rotation, but they drift, sometimes by minutes, sometimes by hours. If the magnetic field is filtered through moving layers, the radio source may shift with them, changing our sense of time. The planet's day, measured by light and by magnetism, may differ because each layer spins at its own speed. We are listening to a duet and mistaking it for a solo. Another theory suggests that the dynamo itself may operate in shells. The outer metallic layer could rotate almost in sync with the atmosphere, while deeper regions churn at a slightly faster rate. Each shell generates part of the field, and their combined effect mimics near-perfect alignment. From space, the sum looks symmetrical, even though the pieces are not. It is the same illusion as two instruments playing opposite melodies that cancel their dissonance when heard together. You can picture the planet's interior as a clockwork of fluids. Each gear moves heat and charge. When their speeds differ, they shear, creating magnetic tension. That tension emerges as a field line curling through the planet and out into space, near the poles. Those lines converge, guiding particles toward the atmosphere, where they spark the cold flame we saw in the last chapter. The auroras are the visible footprints of those invisible lines. At its heart, magnetism is storytelling through motion. Every twist and eddy inside the planet leaves a mark far above the clouds. The symmetry or distortion of that mark reveals the planet's state. A broken mirror tells us there is movement. A perfect one might mean stagnation or a mask. In this case, the mirror may be polished by physics itself, turning turbulence into the illusion of calm. Simply put, we are learning that a magnetic field can lie, not deliberately, of course, but by omission. It shows only what survives the filters of atmosphere and distance. Our instruments measure honesty through distortion, translating the hidden movements of the deep into the language of volts and Gauss. When the translation fails, we must read between the lines. The deeper we study, the more we find resonances between magnetism and weather. The same field that guides particles also nudges the winds. Variations in electrical conductivity alter the paths of jet streams and the heights of clouds. Some storms may feed energy back into the field, closing a loop between atmosphere and core. If that feedback is real, it could explain the radio drift and the stability of the auroras. A self-regulating system, magnetic and meteorological at once, may be the secret that keeps the giant's heart beating. There is humility in this pursuit. Our sensors record numbers, but those numbers come from a world whose true face is always filtered. Every map we draw is an approximation. We can model the field, predict its shape, and still miss what lies below a layer we cannot penetrate. Yet even in uncertainty, the field gives us a way to compare worlds. The tilt of Jupiter, the lean of Earth, the near perfection of Saturn, each a note in a wider symphony of magnetism that ties together the planets and their stars. You might think of the magnetic field as the giant's memory. It retains traces of the past, of formation and cooling, of impacts and shifts. If Saturn's mirror looks unbroken, perhaps it is because the memories are layered too deep for us to see. Only when the currents change will the reflection crack and show the motion beneath. Why? It matters lines follow from this. Magnetic fields govern habitability. They shape radiation belts that can preserve or destroy atmospheres. They guide charged particles that might otherwise batter moons and erase the chemistry of life before it starts. Understanding why one world breaks the rule of asymmetry helps us understand the conditions that allow life to persist elsewhere. To study the field is to study the heartbeat of a planet that will never open itself to us. Each measurement is a clue pulled from silence. Each orbit of the probe is a brushstroke painting the unseen. The result is a picture not of perfection, but of persistence. A magnetic mirror that reflects the hidden dance of matter in motion. When we finally accept that the mirror can deceive, we gain a clearer truth. The universe does not promise simplicity. It promises coherence, and coherence often hides behind illusion. The next question waits just below this symmetry, in the region where magnetism meets gravity and decides which world will be a guardian and which a destroyer. Between the orbits of the inner worlds and the frozen dark beyond lies a titan of gas, immense and silent. To most of history, it has been our shield. Its gravity draws in comets. Its mass scatters debris that might otherwise strike the small blue world closer to the sun. Yet the same pull that protects can also destroy. The giant's influence carves the orbits of countless bodies, sending some inward at lethal angles. It is both guardian and weapon, a sentinel whose strength cannot distinguish friend from foe. Every few million years, something drifts too near. The gravitational tides stretch it, split it, and throw its fragments inward. When one of those fragments strikes an inner planet, the scars remain for eons. In that sense, the sleeping giant keeps balance through violence. It guards the garden by pruning it with stone. This is not cruelty. It is simple physics acting over deep time. Look at its storms. The most famous scar, the Great Red Vortex, has spun for centuries. It rises higher than mountains and moves faster than any earthly hurricane. Around it, smaller storms merge or vanish. The eye is calm, but the rim is wild. A storm like this is not a wound in the planet's body. It is a wound in the planet's balance. It releases energy that has been building for decades. When the storm weakens, another grows elsewhere, part of a pattern that turns chaos into equilibrium. In plain terms, the planet protects by absorbing danger and radiates that energy through weather. Its vast magnetosphere deflects charged particles, forming a bubble that shields the inner solar system. Spacecraft flying near it pass through belts of radiation fierce enough to fry electronics in seconds. Those belts are byproducts of protection. They store what the planet intercepts, holding it until it can bleed away into space. The same magnetic field that keeps the sun's fury at bay is a hazard no craft can ignore. The radiation belts are built from electrons and ions trapped along magnetic lines that loop from pole to pole. These particles circle at near light speed, spiraling endlessly. When a moon wanders through their path, its surface darkens, its ice cracks, its air, if it has any, vanishes. The guardian becomes a destroyer again. The giant's power is impartial. It defends the solar system as a whole, not its individual members. One moon, frozen and quiet, bears the marks of this punishment. Its surface glows faintly in ultraviolet images, scarred by constant particle bombardment. The leading edge is charred while the trailing side stays bright. Radiation has sculpted it into two halves of the same story, one half burnt, one half new. And yet within those scars lies evidence of activity. Beneath the crust, the heating from those same tides may sustain a subsurface ocean, harm and shelter, delivered by the same hand. Think of a blacksmith's forge. The hammer strike that shapes also wounds. The heat that tempers can also melt. Gravity's forge works on worlds as metal workers work on iron, shaping by pressure and release. The giant's gravity pulls moons outward and inward, kneading them like clay. Friction within their cores produces heat, enough to keep water liquid far from the sun. Some of those moons spout geysers through cracks at their poles, jets of vapor and ice that feed the giant's rings. The same violence that grinds rock into dust creates beauty that circles forever. Why does this matter? Because in the exchange between safety and destruction lies the blueprint of planetary systems everywhere. We can see echoes of it in the distant exoplanets that huddle close to their stars. Many of them are giant worlds whose gravity shapes whole families of smaller bodies. The pattern of guardianship and peril is not unique. It is cosmic. The rule seems clear: what can save can also scar. For centuries, we have celebrated the giant's role as savior. It drew in comets. We said, it cleared the sky. But numerical simulations show another side. Its resonances can fling objects inward just as easily as they can trap them. Some of the largest impacts on the inner planets were likely orchestrated by its gravity. The same resonance that sweeps a path clear also sweeps a few unlucky stones straight into harm's way. Simply put, the giant's protection is statistical, not deliberate. It reduces risk on average while amplifying it in bursts. Over deep time, that balance has shaped evolution itself. Without those rare impacts, perhaps new branches of life would never have had room to grow. Without the guardian's heavy hand, the tree might have grown too dense to let light through. The storms above the clouds echo this duality. One side of the planet glows with lightning, flashes that can outshine the sun for an instant. The other side sinks into calm, as heat from within rises. The balance tilts again. Energy is moved, not wasted. The deep layers churn hydrogen and helium like water in a boiler, producing slow motions that surface as tempests. Each storm releases enough energy to power every city on Earth for centuries, but on that scale, it is only breathing. Some spacecraft have dared to fly near the poles, where the magnetic field lines converge. The data from those passes showed enormous currents flowing along the field, connecting the planet to its moons. One of those connections is visible as a bright footprint in the aurora, a circular scar of light marking where the moon's orbit intersects the magnetic sheet. Each moon pulls on the field, and the field responds, creating electric currents that heat both the planet's upper atmosphere and the moon's interior. It is a partnership of charge and motion, a circuit made of giants. At its core, magnetism and gravity work together here as sculptors. Gravity builds the shape. Magnetism paints the surface. One carves the orbit. The other fills it with fire. Together they form a system of tension and release. When that balance tips, a moon cracks. A ring forms. A storm rises. The planet sleeps through all of it, patient as a tide. In everyday language, the giant's behavior is the reason we exist. Its gravity has shielded Earth from countless catastrophic impacts, perhaps allowing life to last long enough to ask why. Yet it is also the origin of many of those impacts. The same gravitational harmonies that protect one world can doom another. The beauty is in the symmetry. A single force plays both roles because nature prefers economy. Why it matters is simple but vast. Understanding how the giant guards and wounds helps us predict how other systems evolve. If we can model how gravity balances chaos here, we can infer how planetary systems survive the early violence of formation. It tells us how long habitable zones remain stable and how many planets perish before life can begin. It is tempting to see intent in these patterns, as if the giant chose to defend. But there is no will in orbit, only consequence. What appears as mercy is merely momentum. What appears as wrath is resonance. The sleeping giant dreams in mathematics, and the shapes of those dreams are orbits, rings, and scars. If you stood above the planet's equator and watched for 1,000 years, you would see little change. The belts would shift, the storms would wander, but the rhythm would stay. The planet would continue to deflect and to pull, to preserve and to erase. To us, it looks eternal. To time, it is a momentary equilibrium before the next balance forms. In plain terms, this is how order survives in chaos. The giant's gravity keeps the system clean enough for fragile worlds to persist, but it does so through cycles of destruction. Our protection was forged in the same furnace that creates storms, rings, and lightning. The sky's safety is never gentle. Every system in the universe may owe its calm to a sleeping giant somewhere, shaping its fate through invisible hands. The trick for any small world is to learn how to live in the shadow of such power, to find stability in the wake of its pull. And if guardians can wound, what do the tilted and toppled worlds beyond them have to teach about scars that never heal? In the outer reaches of the solar system drifts a world that broke every rule of planetary grace. Its poles point where its equator should be. Its day lasts less than 18 hours, yet its seasons stretch across decades. Each pole spends 40 years in sunlight, then 40 in darkness. The planet did not begin this way. Something once struck it with such violence that it rolled onto its side and never stood upright again. Seen from afar, its color is a calm cyan, almost serene. But beneath that calm lies a story of deep trauma. The sideways rotation is not a quirk. It is a fossil of catastrophe. Models suggest that a collision with a body the size of Earth or larger tilted the axis nearly 98 degrees. The impact reshaped its interior and may have rearranged the flow of heat from core to atmosphere. Unlike the elegant balance of other giants, this one spins like a barrel in orbit, its magnetic field lurching far from center, its seasons warped beyond recognition. At first glance, such a world should be frozen, unchanging, lifeless in all motion. Yet its winds move fast, and its storms appear and vanish in flashes. Despite being far from the sun, it glows faintly with internal warmth. That warmth likely comes from the residual energy of the impact and from a slow leaking of heat trapped deep inside. The same blow that knocked it sideways might have sealed heat within, creating a paradox of calm light and restless interior. In plain terms, the planet behaves like a wounded gyroscope, tipped and still spinning, preserving its momentum even as the axis no longer points true. The geometry of its motion affects everything from weather to magnetism. The field does not align neatly with the spin. It is off-center, emerging from a depth far away from the planet's heart. The result is a magnetic system that twists like a loose wire, its auroras dancing at odd latitudes, sometimes far from the poles. Why does this matter? Because rotation and magnetism are keys to climate. The tilted spin changes how sunlight and darkness share the sky, creating extreme differences between hemispheres. One pole bathes in steady light, while the other hides in night for decades. The atmosphere must adapt. Winds shift, circulation patterns bend, and chemistry follows strange cycles of freeze and thaw. Every season here is an experiment in planetary endurance. For scientists, this world is a laboratory of obliquity, a natural test for how planets evolve when their axes fall. On Earth, small wobbles of tilt drive ice ages. Here, the tilt is complete. The equator faces space like a pole, and the poles behave like equators for half a lifetime. The energy balance reverses. Sunlight, weak as it is, hits regions unaccustomed to warmth. Deep shadows linger where frost builds. The cycle of day and night becomes a cycle of decades, and time itself feels stretched. Think of a spinning top that a child has knocked off balance. It wobbles, precesses, and slowly stabilizes into a new orientation. For this planet, stabilization may have taken millions of years. During that time, its internal structure shifted. Layers of ice and gas redistributed. The core may have migrated. The result is a planet with a magnetic field unlike any other one that tilts 60 degrees from the axis of spin and originates near the surface rather than the center. The magnetic irregularity is more than curiosity. It shapes the radiation environment of its moons. Particles spiral along crooked paths, creating spots of intense activity and regions of relative calm. If any of those moons ever held an atmosphere, the field's misalignment would have stripped it unevenly, scarring one hemisphere more than the other. Even now, the strange geometry generates auroras that circle at random latitudes, shimmering in colors that no camera has yet captured fully. Why it matters extends beyond curiosity. The tilted world teaches us that stability is an illusion. Planets can change their posture after formation. Impacts, internal shifts, or resonances with other bodies can roll a world on its side. The lesson applies far beyond our system. When we observe exoplanets with odd light curves or irregular climates, we may be seeing echoes of the same process giants that fell sideways long ago. Some researchers propose that the collision that rolled this world also created a disk of debris that later condensed into moons. The moons now orbit along the planet's equator, which lies nearly perpendicular to the Sun. Their paths prove the event was not slow. It was sudden and massive, rewriting the gravitational blueprint of the system. Each moon carries a trace of that catastrophe in its tilt and composition. Together, they tell a story of destruction followed by reassembly. At its core, this is a tale of resilience. The planet did not shatter. It absorbed the blow, kept spinning, and settled into a new rhythm. Over time, it built a balance from imbalance. Its atmosphere adapted to the strange seasons, finding circulation paths that move energy from lighted pole to dark. The magnetic field, though crooked, remains stable. From chaos came a different kind of order, proof that the laws of motion allow recovery even after collapse. In everyday language, the sideways planet is a survivor. It shows that even a system struck from equilibrium can find a new one. The scars remain, but they define character rather than ruin. Its bluish hue, its calm appearance, all mask the turbulence beneath. The color is the surface of memory. Think of the human-scale image. A spinning globe tipped on its side continues to whirl. But now its continents, if it had any, would experience decades of unbroken day or endless night. Life would have to adapt to extremes, hiding in shadows or basking in permanent dawn. The sideways world turns that thought into a physical reality, an experiment written across billions of kilometers. For scientists who model climate, the data from this planet sharpen predictions for others. They show how winds behave when heat comes from the side rather than above, how polar caps form and vanish, and how magnetic fields evolve when their engines are displaced. These insights stretch beyond theory. They refine our expectations for the many exoplanets that orbit in odd positions, worlds we have only glimpsed through light curves and spectra. Some theories go further. They suggest that such a tilt might not always come from impact. A resonance between a planet's rotation and the pull of its neighbors can gradually topple an axis over millions of years. In this view, the sideways spin is not a scar, but an outcome of cosmic choreography. The same mathematics that governs tides and orbits can rewrite a planet's stance without a single collision. The truth may never be singular. Both impact and resonance may have played their parts. Whichever path led here, the result is unmistakable, a planet that looks tranquil but carries in its rotation the memory of violence. Each turn of its axis is a reminder of that ancient tilt, each season a relic of survival. The sky above it must be unlike any other. From one pole, the sun circles low on the horizon for decades before dipping away. From the other, night stretches unbroken for the same span. In between, twilight reigns, a soft blue glow that never fully yields to day. There is quiet grandeur in that image. A planet spinning on its side, crowned with faint rings, wrapped in turquoise haze. It should not exist, yet it does. It reminds us that even in the coldest corners of the system, motion and accident shape beauty. Its equilibrium is fragile, but it is real. And the lesson it offers is both scientific and philosophical. Balance is not about symmetry, but about endurance. If rotation can be rewritten, then weather and magnetism can be rewritten too. The next world outward will prove that, where cold air and methane form winds faster than sound, rewriting the very idea of a calm frontier. At the far edge of sunlight drifts a world of blue glass and dark storms. It receives barely 1/1000th of the heat that warms Earth, yet its winds scream faster than sound. Here, the sun is only a bright star, its warmth a rumor. The air should be still, but instead it races. Clouds tear across the horizon at 2,000 kilometers per hour. This is the planet where the wind outran the sun. Seen through a telescope, it looks calm, a pale sapphire disk, beautiful and cold, but every frame hides motion. High clouds whip from west to east in bands that shift colors from turquoise to deep indigo. The entire atmosphere is alive with power that cannot come from sunlight alone. Energy must rise from within. from some buried furnace left over from formation. Yet there is another piece to the puzzle. Chemical reactions in the atmosphere absorb light in strange ways, turning heat into motion rather than warmth. The result is a world where air becomes an engine. In plain terms, this planet is too far from the sun to explain its speed, so something inside is driving it. Deep below the clouds, heat seeps upward through layers of hydrogen and methane. Convection carries it toward the upper air, where it meets frigid space. As it escapes, it creates temperature gradients, and those gradients become wind. The difference between equator and pole may be small, but the rotation stretches it into jets that wrap the entire planet. How fast can wind go before it breaks? On Earth, the limit is friction, mountains, and air density. Here there are no obstacles. The air is light, the gravity strong, the path endless. The planet spins once every 16 hours, fast enough to fling equatorial regions into perpetual motion. The winds lock to this rotation, feeding on it. As internal heat rises, it meets the rotation and forms a perfect storm machine. Every puff is accelerated by the next, a relay of force that never stops. You could imagine standing on a floating platform there. The sky would glow a dull blue, the sun a tiny coin above the horizon. Around you, invisible rivers of gas rush by faster than any jet. Sound would not travel the same. Air pressure would crush your ears, and the horizon would shimmer with streaks of haze. Somewhere below, hidden from view, the planet's core radiates the heat that keeps this engine alive. Simply put, the world burns from within, but quietly. Its storms are fueled by a slow release of ancient energy. Long after formation, gravity still squeezes the interior, converting contraction into heat. That heat rises, and when it meets the outer atmosphere, it lifts parcels of gas that fall again, creating a cycle of convection. Each loop drives another gust, and the whole system feeds itself. There is chemistry at work too. Methane dominates the upper clouds, absorbing red light and reflecting blue. Deeper down, hydrogen and helium mix with traces of ammonia and water. Sunlight, faint though it is, triggers reactions that break molecules apart, forming hazes that capture heat. These hazes change how energy moves through the air, trapping warmth where it should escape, forcing currents sideways instead of upward. The imbalance gives rise to jet streams that circle the globe with little resistance. Why does this matter? Because such winds reveal how planets regulate energy when light is scarce. The rules that govern this distant world apply to countless others orbiting faint stars. When we observe exoplanets that glow brighter than expected, we may be seeing similar internal furnaces wrapped in fast air. The wind that outran the sun is a lesson in endurance even in darkness. Motion finds a way. For scientists, each storm is a diagnostic. When a bright spot appears, it tells of heat leaking from below. When it fades, it means that the flow has changed or the convection has paused. Watching these storms over years shows how the planet breathes. Some regions stay calm for decades. Others ignite and die within months. Patterns shift, but the total energy remains astonishingly constant. This consistency means the heat source is stable, not a burst, but a steady candle inside the giant. Think of the planet as an immense cauldron, with the lid sealed tight, the interior simmering, gases rising, condensing, and sinking again. The top cools, the bottom burns, and in between lies a layer where energy struggles to escape. There, chemical compounds change phase, releasing or absorbing heat in pulses. Each pulse feeds the wind above. It is a slow, planetary heartbeat, translated into motion. At its heart, the mystery of this world touches our understanding of time. The storms we watch today may last longer than human civilization. A single vortex can persist for centuries. The rotation and internal heat balance each other so precisely that the system behaves like a perpetual engine. The energy it radiates into space is almost equal to the energy it produces within. The difference becomes motion, an infinite dance of gases circling a frozen sun. If you were to drop a probe into those winds, it would fall for hours through layers of methane ice, hydrogen fog, and storming cloud. Pressure would rise until the craft cracked, and the fragments would be carried away like dust. Yet for a brief time, the sensors would record data showing temperature gradients sharper than any earthly storm. They would confirm that deep convection, not sunlight, powers the violence. It is proof that heat from birth still drives weather long after light has faded. In everyday language, the planet is a lantern without a flame. It glows faintly in infrared, shining more heat than it receives. This excess betrays the furnace inside. The outer calm hides a deep turbulence that never sleeps. Even as the sun's energy dwindles with distance, the interior compensates, feeding warmth upward. The balance of cold and fire produces beauty, a blue sphere that seems tranquil but is in constant revolt. Human-scale analogies can only hint at it. Imagine standing by the sea on a cold night while warm currents move beneath. The surface feels icy, yet the waves rise from energy hidden below. The wind chills your skin, but it was born of warmth you cannot see. That is how this planet behaves, an ocean of gas layered over heat that refuses to die. Why it matters lines form naturally here. These winds teach us that sunlight is not the only architect of weather. Worlds can sculpt their climates from inner energy, spinning storms out of the memory of formation. They also teach humility. The physics that drives a jet of methane on this distant world is the same physics that drives a gust on Earth. Change the scale, and the same equations unfold into grandeur. There is more at stake than meteorology. The speed of these winds sets the stage for how a planet sheds its heat. If they ever slow, the balance shifts, and the world cools rapidly. If they strengthen, internal energy may rise wider than it can escape, building pressure that could alter the planet's shape or magnetic field. The dance between rotation and radiation defines its lifespan. You can see the traces of that struggle in the faint bands that cross the surface. Each band is a track of flow. When they shift, the planet's brightness changes. These variations let us measure its rotation even from far away. In that way, light becomes a stethoscope, detecting the rhythm of a world we will never touch. At the philosophical level, there is a quiet meaning in this. The planet lives in darkness, yet it keeps moving, warmed by what it carries inside. It reminds us that not all motion needs the sun. Sometimes, endurance comes from within, not from external light, but from the memory of creation itself. And if winds can rewrite the laws of motion so far from the sun, what could they tell us about the next world outward, where distance deepens into mystery and silence hides the final record of everything that ever burned? The spacecraft had orbited the giant for 13 years, its sensors tracing gravity, light, dust, and wind. Each circuit was a letter home, a pulse of data through the deep. When the final plan was drawn, the engineers knew the ending. The craft would not be left to drift, nor left to infect an untouched moon. It would dive into the planet it had studied, sacrificing itself to gather one last truth. On that morning, the signal began strong. Telemetry scrolled across screens: temperature, speed, magnetic flux. Each second, the craft sank deeper into thicker air. It had been built for vacuum, yet here it became a meteor. The antenna pointed to Earth until the atmosphere bent it. Engineers on the ground watched the signal climb in frequency as the falling probe accelerated. Then the line began to wobble. Static grew. Numbers dissolved into noise. For a final heartbeat, the data rate spiked, then silence. The spacecraft was gone. To those who built it, that silence was not emptiness. It was the sound of completion. In its last minute, the probe recorded composition, wind speed, electric charge, and temperature higher than any sensor had endured. It measured where theory had guessed. The craft's death was not a loss, but a trade one body for a library of facts. Each packet of information, compressed and transmitted through boiling hydrogen, became a page in the last archive of a falling craft. In plain terms, the dive gave us what orbit never could. From high above, we can see only surfaces and fields. From inside, we can feel texture. The probe's instruments read density directly, proving that the upper atmosphere was more turbulent than expected, that layers mixed in strange ways, and that charged particles spiraled along lines invisible to light. For decades, we had modeled this region as calm. The data showed chaos. Why does this matter? Because without it, our understanding of the giant's energy budget would be guesswork. The temperature readings near the entry point showed heat far greater than sunlight could cause, confirming that the planet radiates more energy than it receives. That confirmation sealed an argument older than the spacecraft itself. Internal energy, not external light, drives the world's weather. The falling probe turned hypothesis into evidence. As the craft descended, its instruments recorded bursts of electricity, flashes of static lightning sweeping through hydrogen clouds. These discharges hinted at storms so vast they could engulf Earth 1,000 times over. The noise came in pulses, rhythmic like the beat of a drum. The scientists watching the data called them heartbeats, a poetic term for precise phenomena. Microsecond flashes marking the collision of ions and droplets. The giant had spoken through thunder. Imagine being inside that descent. The sky would darken from pale gold to black. Pressure would rise until it felt like diving under 1,000 oceans. The hull would creak, then melt. Around you, gas would glow faintly from friction. There would be no horizon, only cloud upon cloud, all moving faster than any wind on Earth. Instruments would tick until their limits failed. Then they would stop. The probe would continue downward, disintegrating into the air it once studied, leaving behind nothing but data racing home at the speed of light. The data stream was not long, but it was dense. From it, we learned about helium rain, the slow condensation of that element deep inside the planet, releasing energy as droplets fall toward the core. That process, unseen before, may explain why the planet's interior remains hot. The same rain may exist on other giants, both here and around other stars. Knowing this changes how we model gas planets everywhere. Some of the final readings tracked dust density near the inner edge of the rings. The numbers showed fewer particles than predicted. The gap between ring and planet was cleaner, emptier, and more magnetic than expected. That emptiness spoke of gravity's relentless pull. The rings are shedding mass, their particles drawn inward by slow drag through plasma and radiation. In the long future, they will fall into the atmosphere, just as the spacecraft did, ending their lives as faint streaks of heat. The dive mirrored that destiny. The probe's fall was the rehearsal for the ring's disappearance. There was a human dimension too. In the control room, silence followed the last signal. Engineers who had worked half their careers on the mission sat without speaking. One of them said later that the room felt like a cathedral after the candles are snuffed. The worship was not of machinery, but of understanding. The end of the craft marked the end of ignorance. We finally knew what it felt like inside a planet that hides its heart. Think of the metaphor: the mission left behind knowledge, written as fire. Every layer of the atmosphere was a page, each measurement a word. As the probe fell, the words burned, but not before they were copied and sent home. The archive was not paper but photons, not ink but electrons. It will outlast the machine that made it. Why it matters extends further. The final data allowed us to refine how gas giants form, how they age, and how they die. The temperature and composition profiles inform models of planets we will never visit. They tell us how heat moves through hydrogen, how rotation shapes magnetic lines, and how storms exchange energy between layers. This is not just history. It is a map for future worlds. The paradox is that destruction gave birth to clarity. To learn what a world is made of, we had to send something fragile into its heart. The lesson repeats across science to measure truth. You must risk loss. The spacecraft became an act of faith in reason, its fall a proof that curiosity is stronger than fear. In everyday language, the final minutes of the mission remind us that even in loss, there is gain. The probe's body burned away, but its mind, its memory of measurements reached us intact. The act of falling became a form of giving. It traded its existence for insight. It was not failure. It was translation. Matter turned into meaning. The last images before the signal broke showed nothing of the planet's surface. For there is no surface, just gradients of gas, light scattering through layers that deepen to infinite pressure. The colors shifted from amber to crimson, then to black. In those transitions lay the story of depth itself. The deeper the fall, the older the material, the closer to the original matter from which the planet formed. In that sense, the descent was also a journey back in time. At its core, this chapter is about transformation. A machine became a messenger, then a memory. Its orbit decayed, but its information ascended. That paradox mirrors the universe's oldest rule: energy never dies. It only changes form. The data lives now in servers and in minds, replayed in simulations and echoed in designs for missions yet to come. Human beings measure significance by endings. But in space, endings are exchanges. The rings will one day fall. The planet will cool. The sun itself will fade. What endures are the patterns we decode before silence takes hold. The last archive of a falling craft is a reminder that even as things vanish, their information survives, whispering across centuries. When the probe's signal stopped, Earth turned its dishes away, but the light it sent continues to drift beyond us. Faint and persistent, somewhere in that signal is the echo of the final packet, the one that carried the last truth a machine could speak. It is still moving outward through the galaxy, expanding the circle of what we know. And what did we keep? And what must the next mission dare to lose when it follows the path of that last archive into the depths once more? Every orbit and every fall in the story of the giants has been a meditation on time. Their winds, their rings, their fields, all exist in a scale that human senses cannot hold. What looks still to us is only slow. What seems eternal is only patient change. The machines we send become our seconds, ticking against the minutes of a planet, the hours of a system, the eons of the sun. The data they return is our only proof that time itself can be measured through motion, that a world's heartbeat can outlast its maker. When the last probe fell, its silence did not end the conversation. The signal crossed the solar wind, passed the orbit of moons, and merged into the background hum of the universe. Somewhere, its last photon still moves, carrying the evidence of a planet's breath. What remains is not the metal that burned, but the meaning it carried. In that sense, science has always been an act of translation, turning matter into story, heat into pattern, distance into understanding. If rings can remember and fields can lie, then perhaps memory and illusion are parts of the same truth. The planets we study do not change to please us. They change because they must. Their balance between gravity and heat, between spin and stillness, is not a metaphor. It is a law. Yet we find ourselves mirrored in them. We too guard and wound, tilt and recover, burn from within and glow in cold. Each giant is a reflection of our own endurance written in gas and light. In plain terms, the universe is not speaking to us, but it leaves enough clues that listening becomes its own reward. Every measurement, from ring vibration to magnetic drift, is a fragment of a larger sentence. Reading that sentence requires patience longer than a human life. That is why we build archives, why we name our machines, why we send them to die inside clouds. They are our extension into a timescale that would otherwise forget us. When we look at the gas giants, we see contradictions that hold together, a field perfectly aligned yet alive, a ring that fades but records, a wind that races in darkness. These are not errors. They are proofs that balance can wear many shapes. The universe is not fragile, it is complex. Where we see disorder, there is design born of necessity. Where we see chaos, there is structure waiting for an observer to find it. The Cassini dive, the magnetic paradox, the sideways planet, the cold flame, all of them whisper the same lesson. The closer we look, the more the boundaries between destruction and creation blur. The line between loss and discovery vanishes. Knowledge is not a ladder we climb once. It is a tide that lifts and falls, taking us with it. Why? It matters is not about the data alone. It is about meaning. In studying these worlds, we confront the idea that stability is temporary. The rings will fall. The storms will calm. The fields will fade. Even the sun that feeds them will dim. But the patterns we uncover remain. They echo through our understanding of other systems, other galaxies, perhaps even the invisible architecture of existence. Every equation written in those missions extends our memory further than flesh can travel. There is humility in knowing that planets move without caring who measures them. Yet there is also hope, because through the act of measuring, we carve significance into the indifference. We give weight to curiosity. The silence of the giant worlds is not cruelty. It is an invitation to learn the language of reality, one rhythm at a time. Some say the universe is indifferent, that it does not notice the eyes turned toward it, but indifference can coexist with beauty. The glow of auroras, the trembling of rings, the whisper of falling dust, all these are unintentional gifts. They are what happens when physics and chance collaborate. They do not need us to exist, yet they find meaning because we watch them. At its core, the journey from orbit to descent, from symmetry to drift, from light to silence, has revealed a pattern older than all machines. The giants remind us that endurance is not permanence, that what lasts does so by changing. The wind that outran the sun will one day slow. The ring that remembers will vanish. Yet in their fading, they hand us the shape of time itself, a cycle of creation, loss, and renewal written in clouds of hydrogen and fields of invisible force. The quote that lives near the end of every discovery is simple. Some clocks only exist while they are falling. It is not just poetry, it is physics. The clocks are the spacecraft, the planets, and perhaps us. Measuring meaning while descending through uncertainty. Falling is not failure. It is how gravity teaches memory to matter. Think of the closing image. A distant planet, its rings thinning into mist, its storms winding down. A small signal leaves its atmosphere and drifts outward. Years later, that signal reaches a telescope orbiting another world, and someone translates its pattern into sound. The tone is faint, but it carries a map of a place that no longer exists as it once did. In that echo, knowledge persists beyond decay. So the great experiment continues. The giants still breathe. Their winds still mark the rhythm of deep time. The next craft will dive again, and the next after that. Each one chasing a new question, each one adding a page to the quiet library of the universe. The wonder is not that the universe hides secrets. The wonder is that we keep asking, knowing we will never finish reading the book. And if knowledge itself is the last ring that will one day fall, what new world will rise in the silence that follows?